All right, in this podcast, we're going to talk about how to graph a neutralization reaction. So we've been talking about neutralization reactions where you take an acid and a base and react them in the correct ratios to neutralize them and make a salt and water. Okay, so now we're going to actually generate a graph of this stuff. Understand that what we're actually doing is called a titration. Okay, so titration is basically a graph of a neutralization reaction. I put on the PowerPoint, and I probably shouldn't. I put always. Always is a bad word. It's a naughty word. So I'm going to change that and say graphs usually have a pH on the y-axis and the volume of whatever's being added, the titrant, whether it's acid or base, on the x-axis. Okay? And over here, I wanted to show you like a little picture. So this thing up top, that's called a burette. And basically what we do is we're going to put the opposite. So if we put an acid down here, we're going to put a base up here. If we put a base down here, we're going to put an acid up here. So whatever the opposite is, whatever we're going to use to neutralize the analyte, we're going to put that in this burette, fill it up. We're going to have a known volume that we're going to read. There's volume markings on this thing. And then we also are going to have a known concentration of whatever is in our burette. We call this the titrant. That's what we are titrating with. Okay, now down below here in the flask, what we have down here is our starting solution, our original solution. We will know the starting volume of it because we can measure that with a graduated cylinder before we put it in there. What we won't know perhaps is the concentration. So oftentimes what is put in this flask is something that is an unknown concentration, and because it's unknown, we can use the volume and concentration of this with the volume of that to figure out its unknown concentration. Anyways, more on that later. It's called the analyte, though. So we have analyte in the flask and titrate in the burette. Okay, so when we initially start a titration, all we have is our analyte down here in the flask. So this is before anything has been added from the burette. For our example that we're going to do today, we're going to start with 25 mils of a 0.1 molar HCl solution in our flask down here. That's going to be our analyte. Because HCl is a strong acid, it dissociates completely, so it's going to completely break up in water. So what that means is whatever the concentration of the acid is, that is the concentration of the H+. So if I negative log that to get my pH, so pH equals negative log of the 0.1, then I get an initial pH of 1. So as you can see on the little graph here, we've got a point for pH of 1 when 0 mils of the titrant have been added. Okay, now you also have to understand what is going on at the molecular level. So at this point, we only have a strong acid, so you should just have a bunch of H pluses and Cl minuses in your flask. Okay, so the next point on the curve that we're going to talk about is the neutralization point. So neutralization, as you already know, is when the moles of the acid are equivalent to the moles of the base, and therefore all of your reactants have been converted into the products of salt and water. Okay, now on a titration curve, this is referred to as the equivalence point. So equivalence point is basically neutralization. Okay, it's going to be a sharp, dramatic change in pH on your curve. Okay, now remember that we started with the 25 mils of the 0.1 molar HCl, and we titrated it with the 0.1 molar NaOH. Okay, so first thing we need to do is we would have to determine the volume that we would expect to need in order to neutralize this acid. Well, if we did M1V1 equal M2V2, we'd need 25 mils of the NaOH to neutralize our acid. All right, now because we reacted a strong acid and a strong base, we know that our salt is going to be neutral. So because our salt is neutral, there's going to be no H pluses or OH minuses, and it's going to be at a pH of 7, right? So we know our volume's 25, and our equivalence point is at a pH of 7. So there's the next dot on our titration curve. Okay, now in the actual container at this point, you're at neutral. So all you have is your salt, which is your NaCl, and your water, which is your HOH. So I didn't put water on here, so just understand that it's understood. The water is there. And then you have your Na plus and your Cl minus. Those are just spectator ions here, but they are in the solution at this point. Okay, the next important point on a titration curve that you need to know about is called the half equivalence point. This is a super important point because this is the place where half of your acid has been neutralized by your base. So for that reason, the concentration of the acid is equivalent to the concentration of the conjugate base. Okay? Okay, so for us, what that means in this particular example is that our acid HCl is equivalent to the concentration of our conjugate base. Our conjugate base in this situation is just the Cl minus because Na is a spectator ion. But understand that that's what is equivalent here, okay? All right, so in order to find your half equivalence point, what you need to do is you need to determine the volume for your equivalence. So our equivalence volume was 25, and literally cut that in half. It's literally exactly what it says. So half of 25 is 12.5. So at 12.5 mils is when we are going to be at our correct pH, okay? So if we were to calculate this, essentially what's going to happen is you're going to have 12.5 mils of the HCl left over that has unreacted. And so you find your concentration there of your H plus, and then you get your actual pH for that value. Okay, so far this is what we've got for our titration curve. All right, so what is in solution at this point? HCl is a strong acid, so we should show it all broken up. So I've got 1, 2, 3, 4, 5 H pluses. Okay, and then my conjugate base is going to be my NaCl. Okay, and so for my NAs, I've got 1, 2, 3, 4, 5. There's 5 NAs. And all my CLs are already present. I already have 10 CLs because they're all coming from that H, okay? Alrighty. All right, so the important thing there was to understand that at half equivalence, your acid is equivalent to your conjugate base. Okay, now we're past equivalence. So past equivalence, all of your acid has reacted, and now you're getting excess base. So say you had 37.5 mils of the NaOH, and that's what you had put into the solution with the 25 mils of the 0.1 molar HCl. Okay, so now we're going to have to go back and we're going to have to determine the excess number of moles of OH minus to get the POH of the solution and then to get the pH from there. Okay, so when we do that, we get a pH that's close to 13 at 37.5 mils. So we basically end up with this general shape for our titration curve. In the solution at this point, all of our H plus has been neutralized by our OH minus to form the water. We do still have some NaCl's over here, okay? So my HCl and my NaCl, we're looking at the 25 milliliters, right? So basically I'm still at 0.1 molar, and then this one has been completely neutralized. It was the limiting reactant in this case. All right, so, and then my NaOH, I used quite a lot of it, but I still have a little bit left over. So I have 12.5 mils of it, which, you know, basically ends up giving me half the amount as I have over here for my NaCl. Okay, so I should have excess base shown, so I should be showing the excess OH minuses. And then I have my NaCl's, and they are all neutralized. Okay, so now that I've kind of walked you through the general points that you need to be aware of on titration curve, now we're going to compare and contrast some different types of curves. Okay, so over here on the left-hand side, I've got some HCl and some NaOH that have reacted. So this is what we refer to as a strong acid, strong base titration curve. Okay, now over here on the other side, I have acetic acid and NaOH. So acetic acid is a weak acid. So this is what we call a weak acid, strong base titration curve. So first I'm just going to talk to you about the general shape of them. So please notice that this point right here where like the pH suddenly shoots up, that's that equivalence point that we had talked about before. And then if you have whatever that volume was for our equivalence, so looks like it was about 25 mils. So if we half that, about 12.5. That's your half equivalence. So there's my half equivalence point. So for both of them, there we go. So there's our half equivalence, okay? And then obviously originals, original pHs, right? That's pretty simple. It's either strong acid pH problem or weak acid pH problem. And then you have your excess regions. Up here we have excess OH minus. Okay, so let's talk about the differences and the similarities. So the initial pH. The initial pH obviously should be different. You should calculate it differently because in the first one we're starting with a strong acid, and in the second one we're starting with a weak acid. So we're going to use an icebox on one of them and just straight negative log the concentration on the other. All right, volume to equivalence, that is found the exact same way regardless if it's a strong or a weak strong. Okay, so M1V1 equal M2V2 if it's a 1-to-1 ratio. All right, pH at equivalence. pH at equivalence is going to be different because we're talking about salts that have a different pH. Over here on the strong, we know that our salt is going to end up with a equivalence pH of 7. Over here on the weak acid, strong base, we know that we should end up with a basic salt, which if you notice, this is definitely above 7, so it is basic. So we're going to have to solve that pH the way we would determine the pH of salts typically. All right, volume at half equivalence, same thing. So you're just going to cut the volume in half. All right, pH at half equivalence. The pH at half equivalence is calculated very differently because a weak acid has what we call a buffer region here. And I will get into more detail about the buffer region in another podcast. All right, and then to calculate the pH after equivalence, that is done the same way. You would have excess OH minus after you neutralized your acid. And so you would go ahead and calculate that the way we have before. Okay, so here's basically the summary for how to do strong acid, strong base calculations. So at the beginning of the titration, this is just a straight strong pH calculation, negative log the concentration of your acid. All right. Before equivalents and after equivalents are done very, very similarly. Basically what you do is you determine your moles of your acid and your base, determine who the limiting reactant is, how much of the excess you have left over, and then you're going to negative log it and get either the pH or the pOH depending on, you know, which side of equivalence you're at, and get to the pH that way. Okay, so we have already done all 3 of these calculations. And then equivalence for strong is super easy because it's just 7 every day, all day long. All right, now this one is a little different, weak acid, strong bases. So if at the beginning you have a weak acid in there, so you're going to do a weak acid pH calculation with your Ka and an ice table. All right, before equivalence, okay, so in this region that you heard me call the buffer region a while ago, before equivalence, we have to use an equation, which I have not introduced yet, so I don't expect you to know it yet. But we do have to use a special equation for that region, which we'll get to later. All right, at equivalence for a weak acid, strong base, this is going to be a salt pH calculation. And then after equivalence, this one is done the exact same way as a strong acid, strong base one is. All you're doing is determining the moles of excess OH minus, recalculating the concentration, and then finding your pH that way. So at this point, you've been exposed to all of these calculations except for that buffer region, which we will talk about shortly. All right, so there are other types of titration curves, so I just wanted to make you aware that they're out there, and that they can potentially come up, so you have to think about them differently. Okay, so we already talked about the strong acid, strong base, which is over here on the left. Nothing surprising there. You know, start at a low pH, equivalence is at 7, and then end with a high pH. Okay, but you can also do it in reverse. You can start with a strong base in your flask and titrate it with a strong acid. In this case, basically your titration curve just kind of does a little flip on you, right? So you start with a high pH, and then equivalence is still at 7, and then you end with a lower pH. All right, now the next variation is a weak base titrated with a strong acid. So I've sort of introduced you to weak acids titrated with strong bases. Start with a low pH because it's weak acid, strong base. Equivalence is going to be basic, so above 7. And then we're going to have, you know, excess OH minus up here. Again, buffer region occurs before equivalence. All right, then on the flip side over here, we've got a weak base that we titrate with a strong acid. So starting with a weak base, of course, the pH is going to be basic. And then you are going to go through that buffer region before you get to equivalence. Your equivalence point is going to be below 7 this time because it's a weak base, strong acid, so definitely an acidic salt. And then you're going to end on the lower end of the pH range here when you have excess strong acid. Okay, and lastly, we've talked about polyprotic acids and bases before, but understand that they have titration curves as well. Their titration curves are sort of like multiple titration curves put together. So, like for this one, you see a polyprotic acid. Notice that you sort of see one curve and then you see another. Both of these dots where it shoots straight up, those are your equivalence points, and there are 2 of them. That indicates to us that there are 2 hydrogens on that acid. So, in addition, you also have 2 buffer regions, 2 half equivalence points, 2 all that stuff. Okay? All right, now the opposite of that is the polyprotic base. The polyprotic base can just accept multiple hydrogens. A great example of this is like CO3 2 minus. CO3 2 minus can accept up to 2 hydrogens. So because of that, it's going to make a polyprotic curve. So polyprotic base obviously is going to start with a basic pH. You are going to have, again, 2 equivalence points and 2 buffer regions and 2 half equivalents. Okay, so let's look at this last little example here. So what we're given is a titration curve of 25 mils of 0.1 molar acetic reacted with 25 mils of 0.1 NaOH. So the question is, how would the pH at the starting point and the volume at equivalence change if we used 0.2 molar of the acetic acid instead of the 0.1 molar as graphed below? Okay, so hopefully you should realize that because the concentration of the acetic acid is doubled, then it's obviously going to take double the amount of NaOH to titrate it. So instead of the 25 mils, our equivalence isn't going to happen until we hit 50 now. So at 50 mils is when we're going to hit equivalence. So it's going to double our volume at equivalence because we doubled the starting concentration of our acid. Okay, so let's talk about the pH at the starting point. Okay, so because we have our concentration of our acetic is double, that means that it is going to have some more H pluses coming off of it because the concentration is doubled. So we should expect for it to have a slightly lower pH, but not by much at all. Okay, all right, so the second part wants us to sketch, and y'all know my drawing skills are a little bit special, and I just used the highlighter there. Oops. Okay, so you basically want to follow the same trend here, and then it should have the exact same shape and everything, but it should just take a little longer to get there. Okay, so like that. Okay, so that's my crappy version of the pH curve.